to be talking about surfaces and interfaces, and mainly since this is a quantum condensed matter physics course, I will be dealing mainly with a study of magnetic materials with neutrons, polarized neutrons. And the first thing that we will discuss is neutron reflectivity and how to derive the expressions for it and the various forms for it, and how to analyze the data you get with neutron reflectivity. So let me just go to the first slide. So here is a diagram of reciprocal space, where this is meant to represent schematically the physical surface. Let me just get that. So this is the physical surface, if you like. It's a kind of a hybrid picture. And these are the wave vectors of the incident and the outgoing beam in K space. And we have essentially grazing angles of incidence alpha I and alpha F for the incoming and the outgoing beam. Now, when these two angles are equal, then you have the specular reflectivity, as you know. Angle of incidence equals the angle of reflection. And that means that the Q vector, which, as you know, is defined as, well, in this case, I'm going to define it as Kf minus Ki. Sometimes it's defined with as Ki minus Kf, is along the perpendicular to the surface, the normal to the surface. And so this is called the specular ridge. Essentially, the specular reflectivity is measured all along this line. By rocking the sample and essentially moving the Q vector off the specular ridge, one can measure the off-specular scattering or the diffuse scattering, and one can do that in several ways and along several tracks simply by controlling alpha I and alpha F, or alpha I and 2 theta, the angle of scattering, which is alpha I plus alpha F, independently. And so this is a general Q that is measuring here off-specular reflectivity. Okay, so the next thing I wanted to say, having got the geometry, so as I said, this is the condition for specular reflectivity. Qx and Qy are 0, and as you know, Qz, which is the length of the triangle, if Ki is equal to Kf, it turns out, and alpha I equals alpha F, turns out to be 4 pi over lambda times sine alpha I. Okay, so so what do specular and off-specular scattering measure? As I will explain to you, specular reflectivity essentially measures variations in the scattering density normal to the surface averaged over the xy plane. So it measures a density profile. In the case of nuclear density profiles, it measures that. It can also measure magnetic density profiles, which is magnetization density profiles, which is probably what we're more interested in. Whereas off-specular scattering measures in-plane variations of the scattering density in the plane due to phenomena such as roughness, magnetic domains existing, ordering, stripes, and various other kinds of things. So those all occur in the off-specular direction. Okay, so in magnetic materials, neutron reflectivity is usually, using polarized neutrons, is used to measure magnetization density profiles around interfaces, which gives you a crucial information, especially if you can do this as a function of magnetic field around a hysteresis loop, or if you change temperatures and go through any phase transitions, particularly transitions that begin at the surface or the interface. And there are applications to phenomena that you can study, such as exchange bias, giant magnetoresistance, and many others. So let's talk about the basic equation. This is for X-rays, but it's equally valid for neutrons. So you've got a beam coming in with alpha I, going out with alpha F, and this is specularly reflected here. We're assuming the condition of specular reflection. There's also in general a transmitted beam in the medium, so this is a single, we're assuming a single smooth surface, no roughness, perfectly flat smooth surface, and just two media, vacuum here and a medium here, with refractive index n. Okay? And we take this surface at z equals 0, define this as the x-axis, and define this as the z-axis. Then the Helmholtz equation, both in the free space region and in the medium, can be written in this way: del squared, if this is the electric field, and although the electric field is a vector, we can not worry about that here, because we can consider this the neutron wave function, which is a scalar, since we're dealing with neutrons. This was adapted from a slide for X-rays. So this is del squared psi r plus k squared n squared r psi r equals 0, and that's basically the Schrodinger equation, except that we've rewritten it in a form which involves a refractive index. And I think in one of the first lectures, Professor Broholm derived the expression for the refractive index in terms of the scattering length density. So I'm going to come back to that later, and it also depends actually on the magnetization density. So it's a general function of the magnetization and the nuclear density, and could depend on position. So we write it in this way, and so the problem reduces to solving this equation with the correct boundary conditions, which is that the wave function has to be continuous, and its normal derivative has to be continuous at this interface. So when you do that, you basically get the Fresnel theory of reflectivity. Before I go to that result, let me just say that the refractive index n is normally written as in this form: 1 minus delta r plus I beta r. This is the dispersive part of the refractive index. This is is related to absorption. And this part, I think, as has already been shown by Professor Broholm in his early lectures, I think in his first lecture, is related to the wavelength of the neutron, the scattering length of the neutron, the coherent scattering length, and the nuclear density of nuclei. Now, this product is the scattering length density, and if you've got a bunch of different nuclei with different concentrations, you are meant to understand this as a kind of an average over the different kinds of nuclei, and they're weighted with their relative scattering lengths and their relative densities. So that's the function delta r, and let me just say that delta r is in general a number which is typically quite small compared to 1. It's of the order of 10 to the minus 6. And for positive scattering lengths, you notice that n of r is less than 1. And so you have the phenomenon that vacuum is the optically densest medium for neutrons, whereas solids and most solids are less dense. So you have the phenomenon of total external reflection, on which neutron mirrors and so forth are all based. The exception is when you sometimes, occasionally, you can get nuclei, as you know, with a negative scattering length, in which case this can become slightly greater than 1. Okay, so to go back to now the Fresnel problem, we can just as in elementary optics, we can solve the boundary conditions, and we get simply, as is well known, the Fresnel formula, which says the reflection coefficient, which is the amplitude of the reflected wave divided by the amplitude of the incident wave, is given by this expression, where these represent the incident and transmitted wave and the z component of their wave vectors. And so this is one expression for r, and this is a corresponding expression for t, which is the amplitude of the transmitted wave over the amplitude of the incident wave. Now, the kiz is, of course, the magnitude of k times the sine of the grazing angle of incidence. And because of the two conditions one has to note, first of all, that the component of k parallel to the surface is always conserved on both sides. So that arises from the fact that the wave function has to be continuous. So k parallel for both the incident and for both this space and this space are the same, but kz can differ because in this case there's a refractive index, so we have to use nk instead of k. And when you put that all in, you find that the z component of the transmitted wave vector in the medium is given by this expression, where this is the refractive index and this is the grazing angle of incidence. Now, alpha I is in general small, and so one can use small angle approximations. Let's just go to the next thing. And the reflectivity, by the way, is the amplitude of the is the reflectance coefficient modulus squared. And similarly, the transmission is the modulus of t squared. And operationally, this reflectivity is measured by simply setting a sample up for specular reflection and measuring the intensity of the reflected beam and dividing it by the intensity of the incident beam, assuming that you made all the corrections for background and the fact that you're measuring the same beam areas in both cases. Okay, so that is it's a fairly simple concept and a fairly simple measurement to measure reflectivity, and that's what's done. And so here, more rigorously, if you've got now you can have a medium that's layered, so it's got n layers, and we'll come back to this a little bit later. So let's suppose you're in the jth layer and you want to consider what the component of the wave vector transmitted in this layer, what its z component is. So you can write that as the one coming in from free space, from the air, k incident z component squared minus 4 pi times the scattering length density in the jth layer to the 1/2 power. And so you can see, if I go back to the previous slide, you can sorry, one more, that at some point this thing could become imaginary if this becomes greater than n squared. And the condition for that to happen corresponds to when you've got an imaginary transmitted wave vector, that means you've got an exponential evanescent wave decaying in here, and you've got the phenomenon of total reflection. And if I go back to my slide from before here, when you make the approximation that delta is small and that n is very close to 1, you find, and that the sine alpha is very small and equal to alpha, that the critical angle for grazing incidence for total reflection is given roughly approximately by square root of 2 delta, to a good approximation. And it corresponds, if you like, to a critical Q, a wave vector transfer, which is given by this expression. Again, this is the scattering length density times 16 pi, and you take the square root of that, and that is essentially the critical Q. You notice that the angle, critical angle depends on delta, which in turn depends on wavelength. Okay? So the critical angle is wavelength dependent. In general, the larger the wavelength, the bigger the critical angle. Okay? But QC, the critical wave vector, turns out to be independent of wavelength. Okay, so that's it's a property of the medium, not of the incident beam. Okay, so can we go to the next slide? So here is some calculations of the Fresnel reflectivity using the formula shown in the first few slides. This is putting in a finite absorption value beta, so n becomes a complex number, but it can still be plugged into those expressions perfectly well and used to calculate the Fresnel, what we call the Fresnel reflectivity, which is denoted by why is this thing? So this Fresnel reflectivity is the idealized case of reflectance from a medium which has a completely smooth and flat surface and is completely uniform. Basically, if there's very little absorption, you get critical total external reflection. Reflectivity is 1 up to the critical angle of grazing incidence, and then it drops dramatically and tails off basically like 1 over alpha to the 4th, as you will see. If you've got absorption, this curve gets rounded out somewhat, and you even the region of total reflection, you don't get a complete reflectivity of 1. Okay, can I go to the, so let's go to the next slide. So in order to calculate the reflectivity for an arbitrary, so let me show this on the board here. So we're talking about, for instance, if you've got a surface that looks in profile like this, completely sharp, then the Fresnel reflectivity theory applies. But in general, you may have density profile averaged over x and y. If this is the z direction, okay, and let's say this is z equals 0, you may have something which is a smooth or smeared out profile, or you can even have some oscillations in it or periodicities in it. It can be any kind of density profile. And the question is, it wouldn't be much use to do reflectivity experiments if we were not able to calculate the reflectivity from this. If we could only calculate for smooth surfaces, which hardly ever exist. So the question is how to calculate the reflectivity from basically an arbitrary density profile. Let me write this. So this is scattering length density to distinguish from nuclear density. Okay. To calculate that, I'm going to discuss in the remainder of this first lecture, I'm going to discuss how one can do that. Okay. So one common way to do that, which is approximate, but is quite has the advantage of being more transparent and simple, is to use an approximate formula which is given in the next PowerPoint slide. Which is basically saying that if this if this is the scattering length density, and this here refers to scattering length density, then the Fourier transform of this, derivative of this density, modulus squared, divided by the value of the scattering length density of the substrate deep into the substrate, modulus squared times the Fresnel reflectivity, essentially is a good approximation for the reflectivity for an arbitrary profile rho of z. Okay, so the question is, how is this formula derived? Well, it's only derived in, it can only be derived in the limit when QZ is very large and you write down the asymptotic expression for R Fresnel, and then you use the Born approximation, which you've already probably been has been discussed in previous lectures. Then you can justify it. But of course, when you get close to the critical angle, the Born approximation breaks down. Nevertheless, by calling this the Fresnel reflectivity rather than the asymptotic form, you still manage to capture to a large extent the features of the actual reflectivity. And so this sort of works over most of the regime that you're interested in. But as I said, it is approximate, and it's not completely rigorous. It cannot be derived rigorously. Nevertheless, it's instructive to look at this formula and examine it for certain special cases which will illustrate the structure of reflectivity curves, which I want to bring out next. But let me, before moving to that, let me just say one thing. Normally, the scattering of neutrons is weak, and you calculate it in the Born approximation, or the kinematic approximation as it's called, and it's just related to the Fourier transform of the scattering length density of the object. And so it's a fairly simple, conceptually, a very simple expression to calculate the scattering. But one has to remember that that is a weak scattering limit. And when you get close to the critical angle, you've got reflectivity which is approaching 1, and that's certainly not weak scattering, because it's getting close to, it's 100% scattering. And so one has to use methods that transcend the Born approximation if one is to calculate that accurately in the vicinity of the critical angle. When the reflectivity is dropped so that it's relatively small and the scattering is weak, then the Born approximation and everything else all converge to the same result. This expression tries to patch up the Born approximation so it sort of works near the critical angle. I will, after this, go on to give you a more rigorous way to do a sort of a, what they call a dynamical theory for the calculation of reflectivity, which is in principle as accurate and rigorous as you want to make it, at the expense of some computation. The second thing I wanted to say, where did my arrow go? Oh, there it is. It's escaping. The second thing I wanted to say is that you notice that this, the reflectivity, has the form of a modulus squared. That is unfortunate, because if it wasn't, this would just be the Fourier transform, and it would be trivial to get the density profile by simply taking R over RF and basically Fourier transforming the result back. A simple Fourier transform would yield for you directly the density profile. Unfortunately, nature is not that kind to us, because it gives us the modulus squared that we observe. And as you know, what this usually means is that we are missing phase information. The phase of the reflectivity is not measured, only the intensity. Now, nowadays, there are many ways around this phase problem, and reflectivity is no exception. But so there are rather sophisticated schemes to go from measured reflectivities back to the density profile using phase retrieval methods, or attempted phase retrieval methods, and other methods, which I will talk about later. But right now, I'm just going to talk about a rigorous method of calculating the reflectivity, and which usually involves a few parameters for the system that you're wanting to study, and then least squares fitting those parameters to the measured reflectivity, which is the common way to analyze reflectivity data at present. Okay, so can we go to the next slide, please? So I think I've explained everything here. Let's go on. So let me give you an example of using this formula to show you qualitative features of reflectivity curves. For instance, let me go back to the board here and show you again. Where did I put my pen? Oh, I put it in my pocket. Okay, so instead of a smooth surface, let's suppose, I've illustrated it here really. Instead of a smooth surface, let's suppose I have, here's a smooth, let's suppose this is the z direction now. I'm looking from the side and this is up. If I've got a smooth surface, the profile is just a flat line. If it's a rough surface, in general there'll be some random, often Gaussian fluctuations of this surface about that point, about that line. And if I XY average and take a density profile, in general this will correspond to a uniform density inside, which will gradually and continuously tail off, okay, to a zero density by the time you get above the highest fluctuation, if you like. So the density profile, in general, if I plot it this way, z increasing like this, here's the substrate, we're coming to the roughness, it starts to tail off this way, and in general, if these are random Gaussian fluctuations, which nature often makes roughness in that way, this thing is the integral of that, which is an error function, right? So it's an error function, and so I can represent the profile as an error function centered around z equals 0 with some kind of width, a characteristic width of that error function, which I call sigma. Okay? So now let's go back to the slide and see what that does when I put it into the master formula that I had. So here is the, here I can write the density as rho infinity times the error function. So when the error function is defined as at z minus infinity, it's 1. At z plus infinity, it's 0. And at z equals 0, it's a half. So it goes from 1 to 0. It's not always defined this way, but sometimes it's defined as going from 1 to minus 1. But I'm defining it this way. It's just a matter of a constant. If you take the derivative of this, since this is the integral of a Gaussian, you get minus rho infinity times e to the minus z squared over 2 sigma squared. It has to be negative, you see, because the derivative is negative as you go across 0. So when you differentiate it, you get this, and now you take the Fourier transform to get this expression here, and the Fourier transform of a Gaussian in 1 dimension, or actually in 3 dimensions, is a Gaussian, and you get this expression. And then when you modulus square this, okay, then it turns out that when you divide that by rho infinity and modulus square it, this factor of 2 goes away, and you just get the Fresnel reflectivity times e to the minus qz squared sigma squared. So what that tells you is that you can describe the scattering, the specular reflectivity from a rough surface in terms of the roughness parameter sigma by kind of like a Debye-Waller factor, which I think Professor Egami has already introduced in an earlier lecture, times the Fresnel reflectivity. That's how it modifies it. Can I have the next slide, please? So you can see that this is what happens if you want to calculate the reflectivity. Here's the sharp interface, which is the Fresnel curve, the solid line, and all these represent different approximations for the profile when there's roughness present, and one of these is the error function. But they're all pretty much the same. Different types of error functions and a hyperbolic tangent profile pretty much give you all the same results. Okay, so, and that's for this typical value of sigma, 10 angstrom, root mean square roughness, and a wavelength of 1.54 angstroms. This happens to be because it actually refers to an X-ray measurement, but there's no difference between X-ray and neutron reflectivity measurements, really, apart from the fact that we can measure magnetic profiles with neutrons, polarized neutrons, as you'll see. So this is the expression here, up there. Okay, let's go on. Here is an experimental measurement, actually with X-rays, of the specular reflectivity from a water surface. And you can see this is the Fresnel curve, and you can see the data actually drops below that. And if you plot R over the Fresnel reflectivity and plot it as on a log scale versus QZ squared, the slope of that will give you the mean square roughness. Okay, and it's like a Guinea plot, and the mean square roughness comes out to be typically for water about 5 or 6 angstroms. Okay, most liquid surfaces have that kind of roughness. Okay, let's go on. The next example I will give you. Yeah, let's go on. So the second example is what happens if you put a uniform slab, a thin film, on a substrate, which itself is also smooth. Roughness can be taken account, as I said, in the way I've just discussed in the usual way. So to avoid having it too complicated, let's leave roughness out for the moment. So let's assume that here we have a scattering density which is rho infinity for negative z, and then for positive z it's rho 0 up to distance d, that's the thickness of the film, and then drops to 0. So this is a density profile if I plot it here, which looks like uniform here, and then a constant density here, and then 0, and this thickness is d, and this is z equals 0. Okay, so so this is a slab, a thin slab placed on a substrate of thickness d, and let's see how it works out using the master formula. So you can see that if I have these sudden discontinuities at the interfaces, give me delta functions in the derivative, and that can be written in this form: rho naught minus rho infinity delta z. If rho naught is smaller than rho infinity, as I've drawn it on the blackboard, in fact this will be negative, as it must be, minus rho naught delta z minus d, where the film ends at z equals d. So one can literally easily analytically Fourier transform this expression, and you get expression like this, which can also be written in this particular way. And then when you put it all together, divide by rho infinity and modulus square it, and multiply by the Fresnel reflectivity, you end up with, by doing some simple algebra, you get this expression R Fresnel, times a term like this minus this term cosine QZD plus 2 rho naught over rho infinity sine QZD. Now you notice that these functions here, cosine QZD and sine QZD, have they're periodic functions. So they have a period which is 2 pi over d, and so they give you oscillations in the reflectivity, which are periodic with a period 2 pi over the thickness of the film. And these are called Kiesig fringes. So it looks like a fringe pattern, and physically it's just due to the interference between the top of the film and the bottom interface, constructive and destructive interference. So it's very similar to what you see in the colors you see from an oil slick, Newton's rings and so forth. Okay, so let's go on. So here's an example stolen from Professor Marjak's lectures to the Neutron and X-ray School in this country, where you can see that he's plotting the logarithm of the reflectivity for a uniform slab, and you can see that you have these very sharp fringes, and they essentially, by measuring the period of these fringes, you get immediately the thickness of the film. So that's something, if you want to measure the thickness of a film, you can do ellipsometry, you can do many other measurements, but a simple way also is, if you have access to reflectometry, is with X-rays or neutrons, to simply measure the Kiesig fringes and you get the thickness of the film. Of course, if there are different kinds of films of different thicknesses on there, you'll get a superposition of all these periods and it'll look complicated. Then you have to do some fitting. I also should mention that in principle, there's always experimental resolution involved. So, you know, your resolution of the instrument is not infinitely good. So there's always some smearing out in Q of these scattering patterns. And if your fringes are very sharp or very close together, they may smear out and you may not see them. So there is a kind of a limit. Since these fringes are spaced at 2 pi over d, there's actually a limit in d over which you can actually measure the thickness. If d happens to be too large, then the fringes are smeared out by the instrumental resolution and you cannot measure the thickness. Typically, this will happen when the film thickness reaches several microns or so, in general. Another way of looking at that, by the way, which is interesting, is to say, well, what sort of part of the surface does the reflectivity actually sample, and what does it measure? And here we come to the question of coherence, which I'll just touch on here. I don't think it's should be the topic of my lecture, but I will just mention it, that in general, a neutron beam, just like an X-ray beam or a light beam, when it falls on a when it's propagating, has a certain degree of coherence where it's phase coherent with itself, and this coherence has a certain extent in the transverse and the longitudinal directions. A simple way to understand coherence is if you have, for instance, if you have young slits, two young slits. As you know, if a beam goes through it, you get the fringe pattern out here. So here's a wave coming in, and you get, as you know, interference patterns, and you get a fringe pattern on a screen at the back. Okay. Now, let's suppose the distance between these slits is d. If you in general, if you move these further and further apart, these fringes will tend to wash out, unless this is coming from a completely coherent source or a point source. And the distance at which you can decide that they're washed out is, if you like, a measure of what's called the transverse coherence length. Okay, And similarly, there's a longitudinal coherence length, which is decided by the monochromaticity of the beam. How monochromatic is it? And is inversely proportional to the wavelength spread of the beam. So in general, neutrons are not extremely coherent objects because you don't want to make them extremely monochromatic or collimated because you lose a lot of intensity, and you can't afford to do that. But in any case, they can be thought of as a finite wave packet which is coherent with itself, falling on the sample and being reflected from it. And so in general, the area so if this represents like a kind of a transverse coherence length, the area which is being sampled for the reflectivity measurements is this footprint, if you like, of the coherent beam on the surface. And in general, if this angle of incidence is alpha I, then the coherence, the effective coherence along the surface is greatly amplified because this beam is spread out. This coherence area is spread out on the surface, and you have to multiply by a factor 1 over sine alpha I to get the projected footprint of this beam, this coherent part of the beam on the surface. So in general, if you had grazing incidence, you can have, in the direction of the beam at least, a fairly large area of coherence where objects can interfere with each other, or you're averaging over that for measuring the specular reflectivity. And that's going to be more important when we talk about off-specular scattering and correlations across the surface. But in any case, it's important to remember that what reflectivity averages over is essentially the coherence area of the beam on the surface. And of course, then different coherence areas, if the beam is bigger than that, are also put into the average. So essentially, you're averaging over the whole surface for reflectivity. So let me just say that let's go on and see what's on the next slide. Okay, the final example, which you can do analytically using that master formula, is to examine the reflectivity from a bunch of multilayers which are periodically repeated bilayers. Okay, so let's suppose, for instance, that one bilayer has a scattering length density which is centered on the position n times a, where n is an integer and a is the periodic repeat distance. So if you sum this from n equals 0 to n, you've got the expression for a periodically repeated set of bilayers, each bilayer having this profile. Okay, and this can be taken to be relative to the center of that bilayer. Okay, and so n goes from 0, z minus a, then z minus 2a, rho of z, then z minus a, z minus 2a, z minus 3a, and so on. You add them all up, and that's basically a function which is rho of z will go essentially periodically. And you can think of the periodic distance a as just a bilayer which is repeated. Okay. So let's go back to that. So let's take the if we take the now the so if we take the derivative of this expression and Fourier transform it, then you can see that I can reduce the integral to just the integral over one period, okay, by shifting the origin for each bilayer and pulling out the corresponding phase factor in here. So it's like doing e to the iqz minus NA, and then rho LZ minus NA, so I can just shift the origin to NA, but then I have to compensate by putting this phase factor outside to make sure that I haven't changed this expression. And so this now is the same for every bilayer. It's just the integral from 0 to A over one period of the Fourier transform of the derivative of that bilayer density, and I call that essentially a form factor as a function of QZ, and it doesn't depend on n. And the other one is just a kind of a block-like sum, but it's not an infinite sum which would give you delta functions whenever QZ would be equal to some multiple times 2 pi over A. Instead, it gives you, when you do a finite sum, it gives you like a bunch of subsidiary minima, which are the Kiesig fringes, times a series of peaks whenever QZ is equal to n times 2 pi over A. So it peaks whenever you're at that, and so let's look at the next slide. So when you modulus square it, you get the form factor modulus squared and this thing squared. We're leaving out the substrate here. It can also be put in easily, just like I did for the thin film. And let's go on. And this is again taken from Marjak's lectures. Did we lose it? Yeah. So you can see that the reflectivity here now has a bunch of peaks. The Kiesig fringes are still there, adorning each peak. These peaks are essentially what are called the multi-layer Bragg peaks. So if you've got a periodically repeated set of bilayers, you've got what you call a multi-layer. It's a periodic structure, and it's just like a theory of a diffraction grating, right? If you've got a finite diffraction grating, you get different orders, n equals 1, n equals 2, n equals 3, n equals 4, and you get subsidiary maxima corresponding to the thickness of the whole film. So the spacing between these fringes is 2 pi over the thickness of the whole film, the total set of all multilayers, and so they're much closer. And the spacing between these peaks, the orders, is 2 pi over the periodicity of the bilayers. Okay? And the reason why they decrease, actually, is because these are not completely smooth. And there's a form factor multiplying it, which is going to modulate it as a function of QZ. But in addition, there's also the Debye-Waller-like factor, which is due to roughness. And so roughness will take down the higher order peaks, and resolution might often wash out some of these peaks, these fringes also. So whenever you analyze reflectivity data, you have to take into account roughness. You have to take into account finite instrumental resolution when you're fitting your data. Okay, let's go on. Now, so this is all based, so you can see that master formula, which is a quasi correct expression, but not exactly rigorous, gave you easy insight. It gave you insight to understanding the forms of the reflectivity for different special cases and how to interpret them. But in actual fact, to do the calculation rigorously, for an arbitrary profile like this, or any other arbitrary profile, we need to use something which is a little bit different. And this method of calculating reflectivity has been discussed for 50 years by, it's in the classic text on optics by Max Born and Wolf, Emil Wolf. Born and Wolf has a discussion of a method for calculating that. And there was a famous paper by Peratt in the 50s for X-ray, analyzing X-ray reflectivity, which used a very similar method. And I'll discuss this method now. Okay, so if you've got some arbitrary profile, like this, let's say, one way you can represent this is as a stack of slices. Maybe you can choose them to be all of the same thickness for convenience, but you have to give them different heights, scattering length densities. So you can, it's like a histogram of the actual curve. Okay, so and by making these slices as thin as you like, you can get as accurate a representation of this curve as you want. But of course, the increasing number of slices, as you will see, leads to increasing computational effort. So you can get accuracy as much as you want for an arbitrary profile to calculate the reflectivity, provided you're prepared to spend more computational time doing it. Of course, nowadays, with the advent of very powerful, fast computers, that's not a problem. So so the only drawback, as I said, is the numerical effort, but otherwise you can get it as accurate as you like from an arbitrary profile. So now I think I think I'm going to go to the board and write down equations which were a bit clumsy to do in PowerPoint. So now I'll switch to the board, and let me just say that when the lecture notes will be up on the web, these notes will be scanned in, so it'll be part of the lecture notes together with the PowerPoint file, so you won't miss anything. So, and I'll define it in this way. So I'll have a surface here. And each surface, by the way, is going to be regarded as completely smooth, because if I make it thin, I can represent some arbitrary profile this way. So I've got maybe a layer under it, and then I can keep going. This dots means continuation, and now I pick out an arbitrary layer inside the stack, and the layer below it, and then I keep going. And then I finally end up with the substrate. Okay, so this substrate here, and the beam comes in here. And is reflected off here. I guess we're not moving around long enough. So it's reflected off there. And let's call these heights, let's call this z equals 0. Well, we could take it 0 here, but we'll call it, so we'll call this z1, z2, and in general, if you've got the j minus 1th layer, we'll call this j, zj. And finally, this one will be Zn, where n is the total number of layers. Okay, so including the substrate. So let's say in some layer in some arbitrary layer in between, we've got a beam going in like this, and a beam going like that, and another beam going like that, and like that. Now remember that at each interface, because of the continuities of the wave function, the k parallels are all the same. At each interface, and equal to that in free space. So we need only describe it in terms of the kz components. So let's call this component above the zj, the interface, we call this k j minus 1, and it's this stands for k in the j minus 1th layer, the z component of its wave vector. and then this would be minus kj minus 1, since its z component is reversed, and this will be kj, and this will be, this will be minus kj, and this will be kj, going this way, okay? So we're writing the wave function in the jth layer as basically we're writing it as ai times e to the I k I z plus bi times e to the minus I k I z, and ki really stands for the zth component of k in the ith layer, and it's actually equal to k naught, the zth component of the wave number in the in free space, minus 1/4 times the critical angle, the critical q for the ith layer. So that's what the theory of to use the condition that the k parallel is the same and that the refractive index controls the magnitude of the overall k, the z components are related in this way, as we've seen before, because k0z is simply k naught sine alpha I, the angle of incidence on the surface, which is also the square root of the incident wave number, its magnitude, minus k parallel squared. And that's constant for all of them. Okay, so now we have this situation where we've got waves traveling this way and this way in each layer. Okay, and now what we have to do is to match boundary conditions. Let's say at this point, Zj. So when we match boundary conditions, we make the field, the neutron wave function, and its normal derivative continuous. We can solve for ai and bi in terms of the one below it. Okay, in terms of ai plus 1 and bi plus 1. So in fact, let me write it. So I can write ai minus 1, bi minus 1. I'm going to write ai minus 1 and bi minus 1 in terms of ai bi. So I'll write this as a 2-column vector, and I can write this as a matrix M of I into a 2-column vector ai bi. So if you like, it's expressing the coefficients of this and this in terms of this and this by this matrix M. Okay, at the so in fact I could have chosen J here, but I could actually have probably chosen I to illustrate, because I'm choosing I here. So these are I's, Ki, and this is Ki minus 1, and this is Zi here at the interface. So I can write the coefficients of the I minus 1th in terms of the ith ones through this matrix, and matching the boundary conditions, and a little algebra tells you that this matrix is written in the following way. It's a 2 by 2 matrix, and it can be written as Ki plus 1 plus Ki over 2 Ki minus 1 times e to the minus I Ki minus 1 minus Ki times Zi, and over here Ki minus Ki minus 1 minus Ki over 2 Ki minus 1. It looks very much like the reflectance and transmission coefficients we derived from Fresnel. It is actually based on Fresnel-like theory for this interface. Ki minus 1 plus Ki Zi. And then here we have Ki minus 1 minus ki over 2 ki minus 1 times e to the minus I ki minus 1 plus ki times zi. And finally, in this one, ki minus 1 plus ki over 2 ki minus 1 times e to the plus I ki minus 1 minus ki into zi. And then this is this 2 by 2 matrix. So you can see that there's certain symmetry here. This term is just the complex conjugate of that one, and this one is the complex conjugate of that one, and otherwise they look very much like the sort of expressions we got from the Fresnel theory. So if this is true, and we can write ai and bi minus 1 in terms of ai and bi, then we can write in term ai and bi in terms of ai plus 1, bi plus 1. We can write those two in terms of the ones below and keep going. All right? So every layer can be expressed in terms of the coefficients of the wave function in the layer below it. And so if you keep going, you just multiply these matrices, right? The next one is multiplies this matrix. So it's mi plus 1, and so on. So, so this can be written as mi plus 1, okay, times ai plus 1, bi plus 1, and so on. You can keep going. So in the end, what you have is that ai, if you go all the way to the end, which means to the substrate, you have ai minus 1, bi minus 1 is equal to a matrix, 2 by 2 matrix xi times the coefficients in the substrate, an and 0. Why did I write 0? Because in the substrate there is no reflected wave, there's only a transmitted wave, and it's got an an coefficient but no b. The b is 0. There's no wave coming back from the substrate. So there we are. There we have it. And xi is simply the product, okay, from j equals I to n of all the mj's. So that's what this is. You take each of these matrices all the way down, and you take the product, and that still 2 by 2 matrices will give you another 2 by 2 matrix, and that's what this matrix xi is. Then the reflection in terms of this, let me rub this out here. How are we doing with time? So in any way, let me just finish this quickly. The reflection for the reflectance coefficient for the ith interface. So this is the reflection coefficient for ith interface is equal to bi minus 1 over ai minus 1. That is the ratio of this wave to this wave. That's the reflectance coefficient from this interface. And you can show that from this expression here, because this is just x11 times an, this is just 21 times an, you can show that this is x21 of I over x11 of I. And so the total reflection is the reflectance from the first interface when I equals 1 modulus squared, which is therefore x21, x21 of 1 over x11 of 1 modulus squared. And that's the final expression for the reflectivity, which you've gotten from this matrix X, and you got the matrix X by simply multiplying all these little matrices for each interface all the way down. And on a computer, this can be made quite fast. There's another way to alternative way to calculate this, which I'll briefly touch. So this is the method of Born and Wolf. And then there's the method of Peratt, which is related, but instead of giving you a matrix multiplication formula, it gives you an iterative formula to iterate to get the reflectivity. So this actually is the way, if you want to make your slices smaller and smaller, you just have more matrices to multiply. And so at the expense of some computational effort, you can make this as accurate as you like. And next time, in my next lecture on Thursday, I will talk about how to extend this to, right now we've just considered a general scattering length density. It can be nuclear, it can be magnetic, it can be a combination of both. So I want to explicitly introduce magnetic scattering. I'll first give you the Peratt method. I'll talk about the limitations of reflectivity, what you can deduce from reflectivity. By the way, when you measure reflectivity, you don't measure it out to Q equals infinity, QZ equals infinity, because it drops very rapidly. So you measure it out to a finite QZ. And in general, you ask yourself, what depth resolution of the density profile can I obtain? And as I will show you, it's related inversely. It's something like pi over the maximum QZ you can measure. And so it's not, you can't measure it to 0.001 nanometers, for instance. You can measure it only determined by your experimental limitations. All right, so I think I'll stop there, and that's enough for this lecture, and we'll continue and finish this up on Thursday, and I'll talk about grazing incidence scattering and diffuse scattering and off-specular scattering as well.